This will go. Okay, hello everyone. Welcome YouTube to our next seminar. Once I get the notice that we are going, we'll get started. The YouTube is good. All right, welcome YouTube, welcome everyone. It is our next water, wetlands and watershed seminar for fall 2025. We have one more after today, right? So this is almost our last one. So it is with great pleasure that I present to you Renee Price. So Renee has been working on her PhD with me for years, but has been able to do so while working full time as a very successful and like wide-ranging environmental consultant. So Renee has done at least 2 jobs at the same time for the past X number of years. I just can't remember the number. It was before COVID. So Renee Price is, what does PWS and CE stand for? Professional wetland scientist, and CE?
Certified ecologist.
Certified ecologist. Okay, so Renee's been working for a long time in the world of environmental consulting and restoration. She is a PhD candidate in environmental engineering sciences and has over 13 years of experience. You also have your master's degree from, you didn't put all this in here, right? You said I was going to remember all of it, but I don't. So you have your master's from USF in ecology, yes?
Environmental science and policy, and then my undergrad from the old new college.
The old new college, yes. So it's been great working with Renee over these past couple of years. A lot of great data about how wetlands work, how sometimes restoration works, sometimes we're not so sure, about how we can actually measure and monitor systems to understand how they are changing and how variable they are among. So this is sort of a preview of Renee's dissertation defense, which is coming up in less than a month. So we are open for comments and questions, and with that, the floor is yours, Renee.
Thank you. Thanks, Dr. Kaplan, and thanks everyone for joining me today. I'm very excited to, after X number of years, bring this data to fruition. It's been a long time coming, so super exciting. So kicking things off, kind of an overview of where we're going to go today. I'm going to start with some wetland background and study motivation, and then move on to kind of the 3 parts of my study. The first one, we're going to touch on hydraulic variation of reference wetlands. Then we're going to delve into some monitoring design, and lastly, kind of bring it all together, looking at hydraulic and vegetation recovery of impacted wetlands. Lastly, we'll wrap up with conclusion and some acknowledgements. So a little background, the star of the show today, not surprising, is going to be wetlands. We classify wetlands strongly based on the presence of prolonged hydrology, which generates a biogeochemical reaction to create hydric soils. These 2 factors together bring in hydrophytic vegetation, so plants that like to have their feet wet, and all together make up the composition of what we know as wetland ecosystems. This unique combination kind of results in a synergy of ecosystem services. These are intrinsic functions that wetlands do to better us and better the environment. These can include things such as water supply stabilization and filtration, buffering coastal areas. I know there's been a lot of chatter about the awesomeness of mangroves as we've been having some awesome hurricane activity the last few years. They also serve as habitat for extensive biodiversity, and this is just a few of the many services that our wetlands can perform. Despite all of these important things that they contribute, there's been a lot of wetland loss, especially over the last 150 years globally. This can be attributed to 2 of the examples we have here. The top picture being wetland desiccation. That's from water levels being lowered. That's catastrophically impacting the way that these systems function. And as a lot of us are really familiar with, especially here in Central Florida, the photo on the bottom, which is wetland infilling due to residential and commercial development. All of these activities, like I've mentioned, kind of remove all the function and utility of these systems. But there is hope for our beloved wetlands. In more contemporary times, we've seen a move towards conservation and protection of these systems. Some examples are preserves, where wetlands that are still intact or mostly intact are being cordoned off and protected to make sure that they'll stay in that condition. We also have seen a development of mitigation banks. So if there are some wetland impacts that are going to be occurring, there's a way to offset and hopefully have some sort of no net loss. Lastly, and kind of the crux of a lot of the work that you're going to see today is the generation of monitoring programs. And that's set protocols to make sure that we're looking at our wetlands that may be impacted and make sure that if any degradation is occurring, we catch it early on. We've also seen the growth of restoration, which is a really awesome kind of thing to see in the last few decades. On the graphic here to the left, we see the ideal desirable wetland state where we have appropriate species and high function. But over time, we can see degradation and ultimately end into a place where we've lost a lot of our functional utility within the system. The idea behind restoration is that with kind of usually some type of manipulation, we can bring a system back up to its desirable condition again. And how we do that is through a variety of different passive and active applications. In the graphic here, we can see a degraded wetland system on the left, and some things that have been done to it, such as hydrologic restoration, vegetation planting, removing exotic species, etc., which ultimately in the after graphic brings us to a better wetland system that is also bringing back its ecosystem services. But that's all great. How do we inform our designs? And how do we know if the ecosystem is functioning? And then how do we measure success in these restoration applications? So this is where the main star of our show today, reference wetlands, kind of comes into play. The idea behind a reference wetland is that it's an unaltered wetland. There's no anthropogenic activities that have changed its composition. So it'll have ideal hydrology and vegetation communities present. So this allows it to serve as a reference condition. So when we're either restoring or creating wetlands, a blueprint to kind of design off of. But on the other side of things, when we're monitoring wetlands, it allows us to ensure that impacts are not occurring. It's setting that kind of threshold or benchmark to show us what natural variation is occurring and to make sure that that's the only change that's happening on our targeted wetlands. So at the end of the day, reference wetlands, they're our gold standard. They're what wetlands should look like before either disturbance or impacts occur. So the reference wetland concept we can see here applied to kind of the restoration ecology side of things is that reference sites act up here in the space of beginning of our project over time in a higher ecological condition than our restoration sites. And ideally what we hope to see over time is this movement of the restoration sites to meet our reference conditions. But how do we get there? We do a lot of monitoring along the way. We look at water levels, so staff gauges, monitoring wells, and even pressure transducers that can record our water levels up to a minute at a time. We also look at vegetation. So we have transects and quadrats, and lastly soil. And as you'll notice the theme here, we're back to our wetland trifecta of the things that make wetlands function and kind of bring them to what they need to be. So a lot of the motivation for my study kind of stems from, well, we need to pick reference sites for these projects, but how do we do it? And then also when we're designing monitoring plans, what kind of guidance do we have? And lastly, what's the interplay between the vegetation and the hydrology over time to make these phenomena happen? A lot of our data gaps are the result of shorter study designs as well as minimal wetland replicates. And a lot of this is just from the fact that it takes a lot of people and unfortunately also a lot of money to do a large scale study. So a lot of what we see is a handful of wetlands for maybe a year in time if you're lucky. This has resulted in a limited understanding of wetland hydrology and vegetation as a whole for our reference systems, but also in this newfound kind of concept of wetland restoration. So some of the kind of higher concepts that we're hoping to kind of go through today are how similar are reference wetlands, how often do we need to assess them, and how do they recover over time? And fortunately for us on today's journey, we're going to have decades of water level and vegetation data from over 400 Central Florida wetlands that are going to help us answer these questions. Underlying this all is my own personal motivation. Getting into consulting, I had the privilege of getting to do wetland monitoring every other week for a set of wetlands. This allowed me to get to know them a little personally. And I found that after time, some of them would surprise me. And while I thought water levels would go up, they actually would go down or vice versa, which led me to realize that some of them have really distinct personalities that didn't quite fit the rest of the bunch. And that's a lot of my underlying motivation for my dissertation. So moving on to our first study, we're leveraging long-term data sets to quantify variability in reference wetland hydrology. So see also, how similar are our reference wetlands? So bringing us back to this conceptual design, we're starting over on the left-hand side of our graphic, the beginning of time, the beginning of our studies. Reference selection at this point is really important, and traditionally we base that on wetland classification type and the proximity. So if we have a project that's going to be either restoring or monitoring, say, a cypress wetland, we try to find one that's a stone's throw away and that is in a similar condition or ideal condition. What we sometimes don't account for is this dynamic range of variability that can happen within our reference wetlands. And this is really the kind of linchpin of this whole part of the study. Our goal here is to evaluate how landscape, morphometric, and or structural influences of our wetlands affect the hydrology within these systems. So hydrology, we're going to consider one of our foundational components of wetlands. They steer our soils and our vegetation. So looking at them as their hydro patterns or ecohydrologic metrics, these are measures of ecological health often used and applied in river situations, where we have 5 primary characteristics of flow regimes that are used to evaluate the health. Here we can see in the hydrograph, here we've got timing, magnitude, rate of change, frequency, and duration. So we've been able to apply this concept into wetlands, and throughout all 3 of the studies that you're going to hear about today, we will come back to these ecohydrologic metrics to kind of set our benchmark for success. And with them, we've derived 14 sub metrics to help us tease out what hydrologic behaviors are occurring. So our questions for study 1, kicking things off, we want to look at how variable wetland hydrology within and between different wetland types is. So are the water levels for Cypress 1 equal to Cypress 2? And how does Cypress 1 match up to Marsh 1 when you're looking at different types? Question 2, which attributes of the ecohydrologic regime are most associated with wetland type? So the Cypress wetlands tend to have different magnitudes than, say, marshes. And lastly, which attributes of wetland morphology and surrounding land use are predictive of ecohydrologic regimes? So how do physical characteristics such as area, perimeter, and depth influence our ultimate water levels? So the data for this part of the study revolve around 30 reference wetlands located in the Tampa Bay area. They're geographically isolated, and we have 4 types: cypress, cypress marsh, and then also wet prairie. For that proximity factor, they're pretty close. The average nearest neighbor is 2.15 kilometers. So with that, we're going to assume that they have similar geographic characteristics as well as climate drivers. We're going to use for our hydraulic data, biweekly water level data from 2004 to 2021. For this, gaps of only 1 reading were linear interpolated. However, if we had a larger gap, either that year or that entire wetland was excluded from the study. So we have a very robust hydrologic data set to work with. So our first question is looking at that variability between different wetland types. So we're going to define within type as looking at wetlands within the same classification scheme. So here we have 4 cypress wetlands, and while these are in the same classification type, I do want you to note that there are different physical attributes here. We see variances in area, perimeter, as well as depth. For between type comparisons, we're talking about comparing 2 different classification types together. So we might look at a marsh system and compare it to a cypress, or a wet prairie to a cypress marsh. But overall, what we want to look at is the hydraulic similarity or difference between these matches. So starting with our methods, we started with the Shapiro-Wilk test to test the normality of our hydraulic data. And not surprising, it was not normal. This is quite normal for ecological data. So that steered us to have to do non-parametric statistics. So we started with a Spearman correlation, which looks at the monthly mean water levels versus the wetland types. So here we have a graphic of our correlations. And you can see here the warmer colors are going to be our lower R values. This is where the correlation is not as strong. So the behaviors of the water levels when you're comparing 2 wetlands, so say a wetland up here versus the one down here, they're not as comparable. The cooler colors, especially when you get up towards the blue, are more behaving more similarly. So taking that within the same classification type approach, we see here that when you're looking at wetlands that are the same, so say here a cypress to a cypress marsh to a cypress marsh to marsh or a wet prairie, that we generally have moderate to high correlations showing that these water levels behave in similar fashions. But I do want to point out these three cypress wetlands at the top. See, these are all warmer colors, and even we have some reds over here, which show really low correlation for two cypress systems that are being compared to each other, which for me was pretty surprising. And what I found is when you exclude these three wetlands from the data set, that the overall R value went up by 0.02. So it's showing that there are some outliers in our data. And if you pick these for your reference system, there might be implications to what your overall success is looking like. Next, looking at that between wetland type classifications comparisons. So this is, say, taking a cypress wetland, comparing it to a cypress marsh or a marsh. We see a lot more of the warmer colors and a lot more red. We're seeing that those relationships are not as high. And that's a lot of following the kind of the traditional literature of why we want to select a wetland of a similar classification type to help get us on the same page, hydraulically speaking. So at the end of the day here, variability exists both within and between wetland types, but even within the same type, there are some misfits out there, so you do have to be cognizant of that. So moving on to a Crystal-Wallace comparison of where we're looking to see if there's any differences between the ecohydrologic metrics as well as the wetland type. First, we're going to look at all wetland types together. So that's putting all the types in one bag and looking to see what our different metrics look like if they're comparable. Not surprising, not comparable. So overall, hydro patterns are not comparable within between wetland types. Now we go back to our more classic example. Well, we'll pick a wetland that's the same type as the one that we're looking for. And I think the most of us would generally think, well, this is where we're going to see rainbows and unicorns. It's going to be great. It was also some more surprising results that of the 14 ecologic metrics that we looked at, the 14 different hydro patterns, most of them are actually different when you're comparing wetlands of the same type as well. So if you're looking at a cypress wetland, 6 of the 14 metrics that you're looking at are going to be different. And so that can be comparing maximums, minimums, averages along the way. So overall, few hydro patterns are compatible even within the same classification type. So to kind of try to parse this out a little bit more, it's like, okay, we have a whole bunch of reference wetlands. What percentage of them are different per metric that we're looking at? So here's a table where you can see our 14 ecologic metrics that are broken out, as well as the cypress wetlands and the cypress marsh. And so, for example, if you are looking at measures of magnitude within these different classification types, 69% of your cypress wetlands are going to be different from another wetland for the maximum water level. And we can see minimum, mean, and median are a little bit more agreeable, where about 25% are different. Cypress marsh, we're seeing similar numbers. Generally, measures of magnitude were the highest discrepancy. The lowest was the timing of events that were occurring. So the Julian day for the minimum water level and the Julian day for the maximum water level, as well as the times they spent in the upper or lower percentiles, generally had a lot more agreements. So converting that to thinking about metrics, so that's the percent of wetlands that were different from each other. So how many metrics, if I look at two wetlands together, tend to be different? Looking at a cypress wetland here on the left, 9 to 13 of your metrics typically would be different, and a cypress marsh 7 or 6 to 7. Found this to be very, very surprising results. So again, that's all looking at wetland classifications of the same type. So overall, we yielded a majority of hydro patterns are actually different on a same level comparison. So next, we wanted to try to figure out what's driving some of this variation that we're seeing. So is there a regime that's more associated with one wetland type over another? And how does this variation follow our a priori wetland classifications? So here we started with the PCA, principal components analysis, where on this graph here, we have all of our wetland types represented by shape and color. So each one is a different wetland. So the smaller dots are all individual reference wetlands, with the larger dot being, or larger symbol, being the representative member for that whole collection, the average. What we can see here, this is PC1, is the horizontal axis, and it is largely being driven by those measures of magnitude, that mean, median, minimum and maximum water level. And that's showing us kind of the space that our wetlands are existing from left to right. On the PC2 axis, which is this vertical axis, we can see it's really driven by the Julian minimum and maximum date, as well as reversals, which is a measure of frequency. And so overall here, we can see that the average points for each of these wetland system types are pretty dispersed throughout our whole PCA here. So what this shows us is that measures of magnitude separate these wetland types. See, our biggest gap is from left to right. Putting this all into a permutational multivariate analysis of variance, or a PermaNova, we can statistically quantify whether or not these are different. And our findings show that the ecohydrology between wetland types was significantly different. And that's what we expected to see from our results that we talked about previously. So now that we know each ecosystem type has its own set of behaviors, what's driving those different behaviors? Is it attributes of their morphometry that are helping that would help us predict this? So here we calculated things such as perimeter and area, adjacent land use, secondary land use, as well as some of our water characteristics such as depth and the edge and bottom elevation. Try to put those together with our ecohydrologic metrics to see if these were steering the ship at all. So on this PCA, we can see that the PC1 is being driven largely by area and the edge elevation of our wetlands, while PC2 is being driven by depth and whether the hydraulic or hydric classification of our soils. And we see that we have a long range of data here along our PC2 axis, and kind of one little outlier guy driving over our PC1 axis. So what we conclude here is that area and depth are driving the type of wetland types that we're seeing here, and that the big separation between kind of these shallower and deeper systems exists on this PC2 axis, which is largely probably attributed to depth based on our classical understanding of wetlands. Again, putting this all into that PermaNova to get those sound statistically significant results. The morphometry between wetland types was not significantly different. So that's suggesting that some of these attributes, they largely overlie other ones, which we can see in a tighter bunch of the data here. So next, to try to tease out how the all these factors are playing in together, we put the whole kitchen sink into an RDA analysis. So this analysis here has our wetland types as well as our 14 ecohydrologic metrics, and it has all of our morphological attributes all put in together. Through forward selection, we were able to determine that only the depth and the perimeter to area ratio was significant in driving the hydrology. And what this showed us was that wetland type did explain 44% of the ecohydrology, so all those different metrics. But 10% of that was driven by depth, and another 3% was driven by perimeter to area ratio. So what these keys are, so these might be keys to trying to determine what reference wetlands are appropriate for your selection. So circling back to our first questions and now some answers. Are water levels for similar wetland types comparable? Not always. There are some misfits that we were able to find. Do cypress wetlands have different magnitudes than marsh? So is there an attribute driven by a different wetland classification type? We did find that wetland type strongly differentiated the ecohydrologic metrics, especially with magnitude. And lastly, how do those physical attributes of wetlands impact their water levels? We found that depth and perimeter area ratio were drivers, but that a majority of it actually was related to classification type, going back to our traditional approach for selecting wetlands. All right, so moving on to study number 2 is integrating monitoring design with ecological indicators. So this is insights from 19 years of wetland data. So going back to our beginning questions, how often do the wetlands need to be assessed? So why do we assess wetlands? Overall, we want to look at the wetland health, and this can be for a variety of reasons. When we're establishing baseline data collection, we're kind of looking at wetlands at one period of time and wanting to understand what they look like and how their kind of health is overall. For the maintenance and threshold criteria that we talked about when we're establishing wetland monitoring programs, this kind of shows us how things are operating on normal kind of frequencies. So if we're hitting a drought and we're seeing wetland levels drop, we're also going to see that in wetlands that we monitor. Lastly, we can assess wetlands and use them as references for success criteria. So if we're restoring or creating wetlands, this is going to help us set hopefully realistic benchmarks for making sure that our wetlands can function properly. So how we assess wetlands, we've got surface water measurements, groundwater measurements, and we also like to look at vegetation. For the purposes of this part of the study, we're going to be looking at data that was collected with the Southwest Florida Water Management District Wetland Assessment Procedure. And as a quick overview here, these are permanently established transects that have 3 zones in them: the transitional zone, outer deep zone, and deep zone. And these are all based on the proximity to the wetland edge and elevation. So the motivation for this part of the study is that we need to collect data for wetlands ecological health, but often how often or how long are driven largely by staff availability and budget in the real world. And guidance is often pretty minimal in literature. So our questions to kind of delve into for this part of the study are: how consistent are hydraulic regimes and plant communities across reference wetlands? So are we looking at wetlands with similar water levels and plants? How many years of data are needed to capture representative hydraulic and vegetation conditions in reference wetlands? So how long do I need to go out there for until I understand what's really happening with this wetland? And lastly, how do hydraulic and vegetation trends differ with varying monitoring frequencies? So how many times do I need to visit a site in a year to understand what's going on? So the data for this study is based on 3 reference wetlands. They're geographically isolated marshes. For the hydrology data, we have weekly water levels from 2006 to 2025. And for 7 years, we actually have hourly data. That we're going to use. We also use those annual vegetation surveys for data from 2006 to 2025. And one thing I do want to point out for these guys is that they are very close together. So proximity should not be a factor in this one. So for our first question of how consistent across hydraulic regimes and plant communities are across reference wetlands, here are our contestants for this chapter. We've got reference 1, reference 2, and reference 3. These actually are 3 different pictures, I promise.
Yeah.
You can see that they're very comparable systems. Overall, physically, the area is a little bit different, but they do have very similar perimeter area ratios as well as depths. So looking at that hydraulic and vegetation consistency, again, we started with that Shapiro-Wilk test, immediately had to go to non-parametric statistics. For the Crystal-Wallace, first we looked at the hydraulic consistency, and again, this is to test whether or not things are different. So here we have annual hydro patterns for the period of record that we're looking at for these sites. And you can see for the most part that there are pronounced trends for wet and dry season for most years. And for most intents and purposes, they are aligned together. So statistically speaking, we did find that R1, R2, and R3 have equal minimum and maximum water depths. But R1 kind of took a left turn here and is different for different than R2 and R3. It has a lower mean and median water level as well as a shorter hydro period. And some of this we can see the phenomenon happening in some of these hydrographs where R1 tends to dive down a little bit deeper in the water levels than the other 2 wetlands. So overall, though, we can conclude that generally speaking, these marshes do have similar hydraulic behaviors. So looking at the vegetation consistency, first we looked at the entire transect together. So that's from the wetland edge all the way out to what we're calling the deep zone, which is pretty much through the middle of the wetland. We were able to determine that for the species richness, reference wetland 1 had a higher species richness than wetlands 2 and 3. We also noticed that that same phenomenon happened in the transition zone. We saw a little bit more of a mix up in the outer deep zone where R1 actually did equal R2 and R3, but R2 is greater than R3. Lastly, at the deep zone, we had all 3 wetlands in alignment, in which all the species richness was equal. So at the end of the day here, we can conclude that there is some more variability in species richness than hydrology. So now comes the fun part of the NMDS. So here we took this first plot is going to be for the full transect. So that's all 3 of our zones, all the plants put in there together. This is looking at plant composition. So how many species do we have and actually what species they are. So each dot on this plot here represents a wetland for a year and all the species that were present at that time. And that's flattening all that information into a 2-scale approach. So what we can see here is R1 in the red, R2 in the green, and R3 in the blue. So comparing these all together through a permanova to try to tell if there's a statistically significant difference, we found that all 3 wetlands, when you look at a holistic level, were equal for their species composition. Delving down to looking at this by zone, where on this plot, we have each color represents not only the wetland, but the zone per year. We found a similar trend that all 3 wetlands were pretty similar in their species composition. So this was pretty exciting to see that overall, we're looking at the same picture on a vegetation scale. So now we know we're looking at the same thing. Our 3 wetlands are pretty in step with each other. They should be a very comparable kind of source of data. How many years of data do you need to look at for each one to figure out what's going on kind of in the bigger picture? Are you looking at an atypical year or kind of a common year? So do you need to just go once, twice, or an infinite amount of times before you can understand its behaviors? So to do this, we did a length of record kind of analysis. And so we start here by selecting randomly 1 year's worth of data. It can be throughout the entire period of record. From this, we derive the upper and lower bounds of the 95% confidence interval. And you'll notice they're pretty big here because we only have 1 sample. So next, we repeat this by randomly selecting 1 additional sample until all the years of data have been exhausted. And we do this for 10,000 iterations. And as you can see here, the confidence intervals get smaller as we approach all years of data. Once we have all years of data, we know exactly what we're looking at. So to find those sweet spots, we look for the intersections of the 95% confidence interval, as well as the 5 and 10% long-term mean. These are kind of our Goldilocks spots. They tell us how many years of data we need to be able to approximate within those constraints. So now applying this to our 14 ecohydrologic metrics, as well as species richness, we can see that in general, largely the same number of years would be required for all 3 wetlands. So kind of a lot of agreement. You can't go to reference wetland 1 and figure out what's going on in 1 year, but the one next door is going to take 5 years. Overall, the measures of magnitude were generally requiring less years than other metrics, but you can still see here that you were looking at still needing at least 2 to 3 years worth of data to get within 10% of the long-term mean, and 7 to 10 to get within the 5% of the long-term mean. Lastly, some of the measures of frequency, as well as duration, require almost the entire data set, which is showing us that there's a lot of inconsistency with that data and a lot of fluctuation that's really hard to capture in less visits. So now we know that there are some atypical things happening within our kind of greater data set. So how many different so how does what you can capture change with how many times you go out to the field? So if you go out once annually, semi-annually, quarterly, monthly, etc., how does that change the overall picture of your understanding of the wetland hydrology and vegetation? So to evaluate the trend variation by monitoring frequency, we randomly generated frequency data sets. We started with hourly data being our baseline we have 61,000 measurements per wetland. From there, we randomly selected daily, weekly, monthly, bi-monthly, quarterly, and yearly measurements to set up our frequency data sets. Next, we derived our measures of magnitude. So we have mean, median, maximum, minimum, and hydro period to help us get a full picture of what's going on with these wetlands. Next, we compared those frequency data sets and their specific measures of magnitude to our baseline data set. So back to that hourly data set, which is super high resolution and it's giving us the best picture of what's going on with our wetlands. We did the top graph here is mean absolute error. We did root mean square error. And lastly, a correlation with the original. This is just kind of a representative plot here, but you can see when we have in red mean, green median, max in blue, and then purple for median. And you can see minimum and maximum definitely have more error than the mean and median. You can also see as we get less frequent with data, the coarser resolution yields more error overall. So going back again to that Kruskal-Wallis test, how do you know if the sampling frequencies are different from the baseline? Here we can see that for mean and median, none of the different monitoring frequencies, this is going from the original data all the way on the left, all the way to more coarse to annual data on the right, that none of these were statistically different than the original data. Despite the different frequencies. Maximum, different story. Here we had statistically different results occurring just at weekly intervals, suggesting that anything over daily, there's a chance you're going to miss the maximum water level. Minimum was a little bit more forgiving. We start to see differences happening around the bi-monthly frequency. And then lastly, for hydro period, we're actually pretty spot on until you got to semi-annual and annual monitoring events. So overall, what we can see here is that mean and median are generally more stable despite differences in frequency, but that minimum and maximum fluctuates with frequency. So this shows that there's some importance not only in how often you're collecting the data, but what data you're really wanting to see. So pivoting back to our questions again, now with some answers. Are we looking at wetlands with similar water levels and plants? Yes, but we did see that there were some vegetation variation in our 3 selections. So how long do you need to collect water level data for and plant data? It can be 2 to 20 years. It really depends on what kind of metric you're looking at, which was very surprising to me. And then, so how many times do I need to visit my wetlands in a year? We found that daily to bi-monthly is going to give you the most accurate picture of what's going on with your system.
11 minutes.
Okay.
With no questions.
Okay. We'll try to work speed through this a little bit. All right. So the last part, wrapping up, and the most interesting part that we're going to get through very quickly. From desiccation to recovery, looking at passive restoration and ecological self-design in cypress wetlands. So how do wetlands recover? So the backstory on this is as populations increase, as we see in this case study for the Tampa Bay area, our demand for water has also increased exponentially. This is water we drink, water we irrigate our yards with. This has resulted in a lot of wetland impacts. We see a lot of long-term vegetation decline. We see subsidence, these are bottoms of cypress roots, as well as a lot of exotic invasives coming in. But remember, there's hope. So here we see this reduction in water consumption in the Tampa Bay area as we brought on alternative sources such as desalination and water withdrawals. And this actually in this part of the study acts as a form of passive restoration. So what we're looking at is starting with the wetlands to the left and getting to the wetland on the right, the before and after withdrawal reduction. So the questions here, I'll just kind of highlight the easy versions of, do we see the same plants over time? Does Cypress 1 and Cypress 2 or have the same plants as Cypress 2? And how do wetlands, or do wetlands now have appropriate plants after restoration? So the data for this, we used geographically isolated cypress wetlands with data from 2006 to 2025. For our vegetation data, we have 19 reference wetlands. That's annual data that we've folded up. We're not using the zones. We're looking at just the transect and we're looking at species presence absence. Hydrology, you'll have to stay tuned, cliffhanger until December. So our first question here is how vegetation communities have changed in 17 years. So from 2005 to 2022. The top pictures here, this is assuming that every time you go out, your picture looks exactly the same. You're getting the same number of species, the same type of species.
For reference systems.
For reference systems, yes. The bottom picture here is, well, maybe we collected a few years worth of data that were very similar, but we saw some ACER pop in on this last year, so we have some differences happening. As there are two scenarios. So looking at these reference community shifts over time, we plot these into an NMDS, and on the x-axis here, we have time, and the y we have NMDS values 1. And what these are showing you is that each dot is again all of those plant species for each year rolled up into one representative space. And what we can see here is generally kind of consistent agreement over time. There is a little bit of fluctuation, but you don't see any major departures over time. So where is some of that kind of variation occurring? Breaking this down to strata, we've got ground cover where we see kind of a lot of variation that does even out over time. A little less in shrubs and pretty consistent with trees, which is what we'd expect to see, especially in a 17-year period. Not going to have a lot of new trees popping up. So overall, we found most of our variability in ground cover, but it's important to note that 2005 was the first year this methodology was adopted. So part of the kind of trend we're seeing here might be refining of technique instead of ecological shifts. So looking at dissimilarity over time, we wanted to kind of take a peek at, like, here's our baseline plant collection. How has it changed since then? And in general, what we saw was that a lot of the dissimilarity increased over time, especially within these first few sample collection events. Here's another example where it was more dramatic in the beginning, but kind of evened off. So overall picture here, what we can see is that all reference wetlands have departed from their baseline survey. So again, we looked at that for the different strata. Not surprising, for most, ground cover was the most variable, trees was the most consistent, but you do have some guys like this where everything kind of moved around a little bit. So overall, dissimilarity tended to be different for ground cover strata. So our next question of, are vegetation communities in cypress wetlands similar? So is the composition similar? So if you have individual wetlands, are they all going to be mirror reflections of each other? Or does each one have a slightly different flavor in the number of plants and the type of plants that live there? So again, we come back to our faithful NMDS plot. And here we can see two distinct groups are starting to form. And you might have caught that in the first plot that we saw where you had those three pink and purple ones above the rest. So this is showing us that most of our reference wetlands, again, each dot represents a year of the species composition, are pretty tightly clustered together. But we do have three wetlands that are existing in this other space, and definitely pay attention to this as we move through the rest of these results. Breaking that down by strata, ground cover, most variation, which we'd expect, trees having the least. The points are right on top of each other, a lot of consistency here, which makes sense for looking at cypress wetlands. So putting that all into Permanova, what we did find is that there's significant differences in reference wetland vegetation community composition. So how vegetation communities in cypress impacted wetlands moved towards our cypress reference wetlands post-restoration. So to do this, we first calculated the centroids of each of the different wetlands. So here you can see all these individual points that represent a year. We dialed them down into one representative wetland point for each one. This also allowed us to identify our three weirdos over here on the side. And then we use that as kind of a reference point of drawing it together, a larger reference plot of wetlands. Overall, we saw kind of four different phenomena happening. So on this plot here to the left, all these little gray points are all our different wetland points every year for our reference wetlands. Those have all been reduced down to these blue dots as a centroid or a representative point for all of our wetlands and all of our plants per year. The red dots here in this little trajectory, which you can see the arrow coming out this way, is where our recovering wetland has moved throughout its recovery process. So this is post-restoration. Where has it gone? This one's kind of a unique example because although an impacted wetland, it still exists within largely the same overlapping space as our reference wetland. And that's what we can see here on this NDMS chart by year. That we have a general kind of agreement with these reference wetlands, this group over to the right. And that these grouping of wetlands over here to the left largely stay on, they're further away distance wise. We have distance over here on the y-axis. So the closer you are to the reference wetlands, the smaller your distance will be. So here's another example of a recovered wetland. This one's kind of fun. You can see it starts over here and it kind of goes up a little bit and it comes down and then ultimately boomerangs back over here to our reference sites. And we can see that representative over here in our timeline plot where our distance slowly gets smaller over time. But I do want to point out again that phenomenon of the two general groups. We have this group over here on the left. And what we're seeing is that as we are moving closer, we're closer to that group on the left over here. But as time moves on, we depart further from this other reference wetland group over here to the left. And again, this is really emphasizing the importance of selecting representative reference wetlands. Lastly, I'll show you the wild card before we zip here to the end real quick. This is an example where the recovery trajectory existed 100% in this separate group of wetlands. So we can see them characterized here as the shortest distance. Oh. So if you had looked at these representative dots in this conclusion, you might have found that your reference wetlands actually hadn't recovered. And I'm going to skip past this guy and this to get us to the end here. So do we see plants the same, or do we see the same plants over time? Generally speaking, yes, on an individual wetland basis. So does Cypress 1 have the same plants as Cypress 2? And do wetlands that are recovering now have appropriate plants? So the answer is a little like lacking to be desired, but the outcome is really dependent on your reference wetland selection. So quick overview of where we went today, coming back to our conceptual diagram here. We started with study 1. Study 1, first we looked at between type variation and we noticed that it's really pronounced. Your comparable wetlands are not very comparable. So looking at between type or within type, the variation can be smaller. We're looking more clustered together, kind of aligned. But on the other side, it can also be very variable. It depends if you pick a misfit or not. At the end of the day, some of our variance may be attributed to depth and a perimeter to area ratio. For study number 2, we looked at the frequency and duration and how that can influence error. So use your artistic brain here a little bit. These are little error bars on our little wetland guys up here. So if you're looking at daily to bi-monthly sampling for more than 10 years, you're going to tend to have some lower error. If you increase that to semi-annual or annual sampling or looking at less than a year, you're going to have a higher error. For study 3, we wanted to look at how recovery, it may follow a slow, steady upward trajectory like our conceptual diagram suggests here. But sometimes we're going to take the scenic route and it doesn't necessarily mean that we're not going to get back to the same place at the end. And a recovery does not look appropriate, say in this example where we're actually looking to like trend down and further away from our reference sites. We might want to take a different look at our reference wetland selection. The reference, we might have that 2 different grouping happening, and then our reference selections are just aligning to other reference sites that we could have selected. So with that, some quick acknowledgements. Thanks to Dr. Kaplan and the Watershed Ecology Lab, some folks at Tampa Bay Water and the Inglewood Water District for a treasure trove of awesome data, and to the many, many consultants who designed and implemented these monitoring programs over the last few decades. And with that.
All right, thanks for that. All right, excellent. So you're right on the dot. If you have to leave for class, that's okay, but otherwise stick around for 5 minutes or so for questions for Renee. Excited to call you Dr. Price soon. All right, so I'll check YouTube. Questions from the room first, and particularly from students.
I was curious why for each study you chose a different sites to look at.
Yes, so the easy one for that is that for study number 2, those were the only reference wetlands that I had that hourly data. We wanted that high resolution to give us a really solid baseline. And that allowed us to kind of do the different frequencies. For study number 3, we had to find wetlands that were both paired in vegetation and hydrology. The hydrology cliffhanger is what is still to come. But ultimately, we're going to look at how hydrology is also shifted in a similar manner, and then hopefully figure out how they work together to get us back to our reference condition. But good question. I want to play with them all too.
YouTube is quiet. Other questions for Renee? Yes,
There was a
AJ?
part that you said, I think it's from study 1, that perimeter area ratio and depth plays a big part in like choosing your reference wetland, or I guess the outcome for the recovered wetland to the.
It's the hydrology. So perimeter area ratio and depth bring us to, might give us more similar hydrology versus just looking at classification type alone. So if you look at a cypress wetland and you have one that's like 10 feet deep and one that's 2 feet deep, they're less likely to react to this, or their hydrology is less likely to behave the same. But if you had a 2 foot and a 2 foot, then they might, based on our RDA, they might behave a little bit more similarly.
So if the variation in time and space of all the reference wetlands is so large, is basically everything's already restored? Like, are you finding that any of the impacted systems are laying outside of that space? And like, how do you say that they're in or they're out? Can you do that on an individual wetland basis and say that one has recovered because it's in the cloud?
Yeah, that's, I guess, what like brings up or begs an interesting question of like, well, did you not select a system it's similar to, or is it still just not recovering? And I did have one of those examples in the scenarios at the end of how it was the trajectory was going. There were a few that do exist completely outside that cloud, and they're not associated with group 1 or group 2. So it's like, are there more flavors of reference out there, or has it not recovered? Which hopefully some of the deep dive into hydrology will help peel that, I think, layer back a little bit, since first we have to bring the hydrology to then ideally bring the plants.
So building on that a little bit, either as a practitioner or a regulator, how do you deal with this now regarding a reference site being your target to say you have achieved or succeeded? What are you gonna, based on your studies results, how do you go and plan to resolve this or suggest we should address this?
Yes, I think I've definitely opened a can of worms there a little bit. I think it may play into, I guess, whether having like how tight your fitness criteria are. Like, do we allow for some more variation, or pay more attention to what metrics we're actually looking at? Are we looking at mean? Are we looking at median? Are we looking at things like maximum and minimum, which might depart more from our overall group? So I think it might be a combination of refining what we're looking at, but also understanding that there is going to be some natural variation that occurs. And it's, I guess, finding that Goldilocks spot between all that. But I think the foundational at the end of the day message is that like just finding the closest one isn't going to be enough to get you to that kind of end place, or at least get one that might be comparable overall.
So I have two question comments. You haven't done the hydrology on the restored yet, is that right?
Correct,
Right.
yes.
So that can explain a lot of what's going on there.
Yeah.
And then the other one, you talked about land use, the surrounding land use, but I didn't see you actually using that.
So it came out to not be statistically significant.
How did you do the surrounding land use?
Based on flux code, it was the different ones that were immediately adjacent to the wetlands that touched the wetland edges, and then the secondary land use beyond that. And I think we used a benchmark of like 150 meters.
So
And we were surprised, because that was one of the things I know I hung my hat on when I was running analysis, and I was talking to David and was like, it wasn't significant, and I was really.
have you heard of the landscape development intensity index?
No.
LDI? Something that we developed here at the center
Mhm.
that actually gives a quantitative number for how intensely land uses on.
Okay.
Landscape, and that may give you something to go on.
Yeah,
LDI.
well, definitely look into that.
Yeah.
I suggest.
She didn't get there.
But my hypothesis was that it was not gonna come out, actually.
Yeah, yours
Yeah,
was, yeah.
so. Okay. Once in a great while,
LDI.
yeah.
Oh, yeah, okay.
Any last questions for Renee? If not, then our last speaker of the semester, does anyone memorize who it is? Anyone know? No, I don't know. So next week we are going to hear from, we've got Eric Stein. He's the department head in biology at Southern California Coastal Water Research Project, talking about balancing environmental flows with consumptive use in a water scarce environment.